Good morning, everyone.
Good morning, Mr. Richard. Good morning.
How are you guys today?
Good. How are you?
Oh, I'm good. Does anybody follow hockey? Yeah, some of us, maybe? Yeah? Anybody watch the Kraken draft last night?
No.
No? No? Good news that Carey Price didn't get picked, eh? Do you have any Habs fans here? Yeah, some Habs fans? Anybody not know what we're talking about? No? Alright, well, if you haven't guessed it.
I don't know what I'm talking about.
No? No? That's okay. It's just sports. It's nothing important. School's more important, right? Yeah. Alright, anybody hasn't guessed it already today that we're going to talk about magnets and magnetism. And the question I got on there, are you stronger than a magnet? I got some magnets up here. Some are small, some are big. Some are meant for different applications, but these are all permanent magnets. And I'm going to pass them around the class and we'll see if you're strong enough to either push them together or pull them apart. See what you think. When you're done with them, you can pass them to your partner. And I'm going to go ahead and start our PowerPoint presentation. So when we talk about magnets, there's different materials that we used. And just looking at these two pictures, can anybody hazard a guess to what type of materials we use? Elliot?
Iron.
Iron? Oh, that's a very good guess. Yeah. All metals are made, or all easily magnetized metals are made from iron, but I was okay with the answer of any metals. So we're going to go ahead and look at all the different types of metals, the three basic categories of metals. Ferromagnetic. Ferromagnetic is a type of metal that is actually easy to magnetize. So some examples of this would be iron, nickel, and cobalt. So just like Elliot said, iron is a very good metal for permanent magnets. Anybody have any questions so far? Go ahead, Isaac or Elliot.
Why are some metals easier to magnetize?
Why are some metals easier to magnetize? Well, that's a good question. It's not exactly an easy one to answer. Does anybody remember grade 8 chemistry? Isaac?
How do you make magnets?
How do you make magnets? Alright, let's tackle one at a time. Does anybody remember grade 8 chemistry? Anybody remember the atom? You weren't taught the atom? You have grade 9 chemistry this year? Some of you do, some of you don't. Okay, we'll do a quick little side lesson just so I could easily explain this. There's probably going to be more questions than answers after I do this. But that's okay, you guys will all be experts in chemistry this year. So an atom, everything comprises of atoms. So if you look deep inside yourself, deep inside this table, in any material, everything is made up of atoms. It's the smallest little molecule. Smallest little thing is an atom. Atom comprised of a nucleus, which has positive charges and neutral charges in it, and there's a bunch of, depending on what it is, so let's pick on iron. It'll have a bunch of positive charges in the nucleus, which are called protons, and neutral charges, which are called neutrons. And around this atom, we'll have a bunch of electrons. And I don't know off the top of my head how many electrons or protons iron has. That'd be a good question for your chemistry teacher. But let's just say on the outside layer, which is called the valence, has 4 electrons in there. The reason why it makes it easier for iron to magnetize is all 4 of these electrons spin in the same direction. So they naturally want to go to a negative charge, and the protons naturally want to go to a positive charge, which gives you your negative and positive ion magnet. And that's why certain metals are easier to magnetize than others. It's the spinning of the outside electrons. Does that cover your, do you understand a little bit better?
Yeah.
Yes, Isaac?
I have no clue what we're talking about.
Okay. Well, hopefully if you are interested in that, maybe we can do a later lesson on atoms and we can explain it a little bit better. How about that?
Okay.
Okay. So paramagnetics. Paramagnetics are metals that are not as easily magnetized as ferromagnetics, but they can be magnetized. So examples of that are platinum, titanium, and chromium. Diagnetics are materials, are metals and non-metals that are not able to magnetize because they don't go through the magnetic flux. These materials are copper, brass, they could be also yourself, they could be this desk. It's just harder for them to magnetize. So magnetic lines of force, just like we talked in the last one, magnetic lines of force are called flux. Magnetic lines of flux repel each other and never cross. Although magnetic lines of flux do not flow, it is assumed they go from north to south. Alright, what does this mean? So if you have a common permanent bar magnet, there's a north and south. And you can't see these lines, but there's these little lines of flux. And they never ever cross each other. And we always assume that these little lines of force flow from north to south. So we always go from north to south on the lines of force. And those magnets that you're just passing around right now, there's this force on the outside, and this force is called the flux. The basic law of magnetism states that unlike poles attract and dislike poles repel. So again, going with our last example where everything flows from north to south, if we have a north and a south coming up to each other, they're attracting, so they're in love, they want to get closer to each other. So that when you're passing that magnet around, that's why they attract, because the magnetic lines of force are attracting each other. And same when you're passing that magnet around and you're trying to put them together, they're repelling each other. They're like my two younger boys at home, the brothers are always fighting, so they don't want to get along with each other. So that's what happens when you have two like poles, they repel each other. Now a compass, for you guys that may or may not know what a compass is, back 100 years ago before GPS was invented, that's how we had to use to get around. So when I was younger, we had a compass, and a compass has a magnetic pole inside of it that always points to the North Pole, to the north. And you'd have to use a paper map, put the paper map behind it, orientate yourself north, and follow the map that way. Now we have this great invention called GPS, which we have a map on our phone. We don't ever have to use a magnet, or ever have to use a compass, sorry. So a compass is a device that shows the cardinal direction. It consists of a magnetized needle or other element which can pivot and align itself to magnetic north. Yes, Isaac?
This is my first time.
That's okay. It's all our first times. It's
Yeah.
my first time right now. So, a compass points north because of the magnet inside it. And why? Because the Earth itself is one great big magnet. Now, I don't know if you guys all remember geography class. If you look at this picture, this is the North Pole. This is North America, this is South America. What would the white represent? Anybody? Any ideas? Isaac?
North?
The North Pole? Where Santa Claus lives? Yeah? And the red would represent, Elliot?
South.
The South Pole. Okay, so what we just learned, that the magnetic flux flows from north to south with these arrows, and that a compass points north. What can you tell me about the true North Pole? What polarity is it? Is it a positive or negative? Elliot?
Negative?
Negative?
Positive.
Why is it a positive?
Because it attracts stuff.
Because it attracts stuff? Does it attract the north part of the needle on a compass? Yeah? Yeah, you're on the right track. Yes, so the compass, the north part of a compass is attracted to the south magnetic pole, and we know that it points towards the North Pole. So the North Pole and the South Pole, the magnetic force is actually opposite. So the true North Pole is a magnetic south, and the South Pole is magnetic north. Right? The lines of flux flow from north to south. Yes, Isaac?
Isn't Mars gonna crash into Earth and scientists are making a ship for a lot of people to go on?
That is a question I cannot answer for you because I do not know. But if you would like to know the answer, I can look into it for you. So this magnetic force that we have around our Earth is good for us. Not only does it help us with directions with our compass, but it stops the radioactive hazard materials coming off of the sun. It actually shields us and protects us from it. So has anybody been up north and seen the northern lights? Do you know what the northern lights are? Yeah? So those particles and that radiation from the sun that's hitting our magnetic field, that's what causes the northern lights. Isn't that pretty cool?
Yeah.
Yeah. Yes, Isaac?
I saw it once before.
Yeah? Pretty cool stuff, eh?
Yeah.
Yeah. I only got to see it once, but it was awesome. What is an electromagnet? So we covered permanent magnets made from steel. Let's watch a video on how to make an electric magnet.
Hi, this is Ben Finio with Science Buddies, and if you want to know what an electromagnet is and how they work, then this video is for you. You might already know about regular magnets. They have opposite poles that attract, similar poles that repel, and they can even attract
Because
other
of the
metal
lines of
objects
flux.
that don't attract each other, like these paper clips. You can also take a compass, which is itself a small magnet, and move it around near another magnet, and the needle will point in the direction of the magnetic field. So how does a coil of wire manage to behave the same way? It turns out that moving electrical charge, or current, creates a magnetic field. Watch what happens when I connect this piece of wire to a battery. It makes the compass needle move just like a magnet did, so we know the wire must be creating a magnetic field. This magnetic field takes a circular shape around the wire like this. However, the magnetic field around a single straight wire is very weak, not enough to pick up even one of these paper clips. You can make the magnetic field much stronger by wrapping the wire into a coil called a solenoid. This causes the fields around each individual turn of wire to add up to make a much stronger, more uniform magnetic field similar to that of a bar magnet like this. However, you'll see that this coil of wire is still too weak to pick up an individual paperclip. To make an electromagnet really strong, you need to add a ferromagnetic core like this iron bolt. Ferromagnetic materials have many smaller individual magnetic domains. Normally, these domains are aligned randomly and cancel each other out. However, in the presence of an external magnetic field, these domains align with each other and the external field, making the overall field much stronger. Watch what happens when I insert this iron bolt into the core of my electromagnet. Now it's finally strong enough to pick up a paperclip. Unlike a regular magnet, an electromagnet can be turned on and off by removing the flow of electrical current. If you reverse the direction of the electric current, you reverse the direction of the magnetic field. To change the strength of an electromagnet, you can change the number of turns in the coil, the length of the coil, the amount of current flowing through the coil, or the core material, all of which would make a great science project. Because they have very low resistance, the wires in electromagnets can get very hot, so you should always disconnect them when not in use. The paper electromagnet in this video was just for a demonstration, but you should not try this at home because the paper could actually catch on fire. To see a variety of science projects that use electromagnets, as well as instructions for thousands of other science and engineering projects, visit us online at www.sciencebuddies.org.
Anybody have any questions about electromagnets? No questions at all? That's great, because we're gonna make one. We're gonna make electromagnet, we're gonna try different size batteries, we're gonna try different amount of turns around the bolt and different size bolts just to see what happens. Right? Everybody have any questions now? Alright, we're just, oh, yes, Elliot?
Do you have all the stuff to make it?
Yep, we're gonna get together and pick it up right now after we go through a couple of shop safety rules, and we'll get right to it. Okay, that's gotta be over 15 minutes, you can cut it.